I've also started recording.
Sure. All right. Uh, I hope that doesn't create much issues.
Yeah.
Okay. So, Upamanyu, we are very happy to have you here. And he's going to talk about his recent work on quantization of JT gravity by path integral method in the second order formalism. Okay. So let's hear you. Bye. Over to
Yeah. Thank you very much. I'm really grateful to the organizers, especially Ayunda, for inviting me and for giving this talk here. I wish I were present at IIT Madras in person, but it looks like it will be a while before we can all do that. So until then, this is the best we have, and uh, let us go on. So the work that I'm going to talk about is, as Arunda said, is on quantization of JT gravity, Jakob Teitelbaum gravity in the second order formalism, and it is based on a work that appeared last month, a joint work with my fellow graduate student Sunil Sake and my advisor Sandeep Trivedi. I would like to request the audience to interrupt me at any point. I would be happy to answer any question. And it's not important that I finish my talk. It's important that I get somewhere. So let us go on. So the first question before we move forward is why we should be studying JT model. And the answers come in many forms. The first and foremost answer is that it's a very simple realization of the holographic correspondence. It's been widely studied in the recent years as an example of nearly ADS to nearly CFT1 correspondence, especially its relation to the Sajdev E. Kitaev model of condensed matter physics has found a lot of attention from researchers working in this area. Then the beautiful thing about this model is that this model is rich enough to provide some interesting insights into gravity holography. And at the same time, it's simple enough so that it can be dealt with in an analytic manner. That's obviously something that we always look forward to. Then one might wonder whether it's just a formal curiosity. And the answer is that no, it's actually intimately connected to black holes that uh, do appear in real life. For example, it is intimately connected to the behavior of nearly extremal black holes, and there's been a lot of work on this, and I have myself worked on relating the JT model to the dynamics of near extremal black holes. And finally, very recently, this model has been used as a prototype to address questions related to the black hole information problem. And there's already uh, great wealth of work being done on the information problem from the point of view of JT model. So with that introduction and no further ado, uh, let us proceed and ask what is JT gravity. So JT gravity is a model of two-dimensional gravity, and it is known, I think, to all the audience that uh, the Einstein-Hilbert action is a topological invariant in two dimensions. So this is the form of the Einstein-Hilbert action. This is something that measures the ground, let's say, for example, the ground state entropy of black holes, and this measures the Euler character of the manifold, how many holes the manifold has, how many involving how many holes the manifold has, and how many uh, handles it has. And so it cannot describe any interesting dynamics. So one has to couple additional matter to the uh, in addition to the Einstein-Hilbert action. So the JT gravity is described by this action, uh, in addition to the topological action, of course, where there's a scalar field phi, which is coupled to the Ricci scalar in this way. And there's also a boundary term, which has this very specific form. And this L2 is a length scale, which we'll call the ADS2 length scale. And we'll be setting L2 to 1 from now on for simplicity of the presentation of the results. So now the first question is, what can we say from this action? So the uh, first thing that we can see from this action, that this in this action, the dilaton couples linearly to this term involving the Ricci scalar. And therefore, from the classical equation of motion, this r plus 2 is set to 0. And therefore, we get r equals minus 2, which is a constant curvature spacetime, or in other words, ADS2 spacetime. And there's also this boundary, which I have denoted by a del here. This del here, it's defined by a constant value of the dilaton, phi equals phi b. Uh, One more comment. I've said that classically the dilaton equation of motion sets r equals minus 2. And obviously, you can anticipate that this will be true even in the quantum path integral as well, because the dilaton simply acts as a Lagrange multiplier in the action. And now let me talk about the Schwarzian action. So on shell, the JT action is actually a boundary term, and actually the resurgence of interest JT model, I mean, began with some work of Almeida Ponsilsky, but most significantly in a seminal 2016 work by Malus and Stanford and Yang. So in this case, I'm talking about the JT model with one connected boundary. And let us take the bulk metric to be that of the hyperbolic disk. So this is the metric corresponding to ADS2. And near the boundary of that ADS2 that I spoke about, in terms of the boundary proper time, we can define this boundary, sorry, I must correct that. So this is the boundary proper time. And this is some cutoff introduced to regulate the theory. And the on-shell action for a definite cutout shape, which is defined by some rho of u and theta of u, which is some cutout shape of the boundary. The on-shell action turns out to be a Schwarzian action, and there you notice that the dilaton boundary condition appears in the form of phi b here, and here's the 2D gravitational constant. And this because the dilaton also diverges near the boundary in like 1 over epsilon, this phi b epsilon is actually finite, and we get the on-shell action, and from here we can read off all the things, all the quantities of interest. Now, this Schwarzian derivative is defined by this combination of derivatives, which has third derivative, first derivative in a very non-linear way. And one interesting thing to mention about the Schwarzian action is that a Schwarzian action has an SL2R invariance. In other words, if you have one particular Schwarzian composed corresponding to some function g of u, then an equally Schwarzian that is equivalent to the previous Schwarzian would be something like uh, a of gu plus b over c of gu plus d, where the determinant is 1, ad minus bc is 1, and so on. So this has the boundary SL2R invariance. So that's all about the classical aspect of JT gravity. Now we want to study the quantization of JT gravity. in the path integral formalism. We wish to study what's called the uh, partition function, and this partition function involves a functional integral over the dilatant field and the functional integral over the metric, and quotiented by the volume of the gauge group, which are the same configurations in the path integrals. I mean, obviously, and we should not sum over the same configuration. And this is obviously the JT action, and this, I should say, also includes the topological term. And we wish to study this partition function with some given boundary conditions. So the work has already been done in the first order formalism. So in a very nice paper by Saad, Schenker, and Stanford in 2019, they quantized this system not using directly the metric, but the Zweibine and the spin connection. And the JT system is cast into a BF type SL2R gauge theory, and they use the elegant mathematics of topological gauge theory and many uh, elegant tools that have been developed in mathematics to study this path integral. And they have found that this corresponds to some double scaled matrix model. But our goal here is to study this quantization in the second order formalism, where we do not go to this Zweibine and spin connection, and instead treat the metric and the dilaton in a direct manner. So the question is, what advantage does it give over the first order formalism? The answers are obviously more than one. So the first answer is that the effect of additional matter fields, which are interesting to study, uh, they are much easier to incorporate in the second order formalism, and which is uh, somewhat obscure in the first order formalism. And one loses, for example, the elegant mathematical structure when one introduces a generic matter. And then uh, the next good point about the second order formalism is that it generalizes more readily to more complicated situations. For example, if we were to do some path integral in higher dimensions, there again, we might not have some sophisticated mathematical tools available. So with this view in mind, it's worthwhile studying the second order formalism. There's a question by Manisha. Yes?
Yeah, I don't know much about this, so can you please tell me whether what is this? What is the difference? What is exactly the first order formalism and the second order formalism?
Yeah, the first order formalism. So in the first order formalism, you do not use the metric directly. Instead of the metric, you use what is in two dimensions. I'm calling it Zweibine, which is the Vierbein. If you are familiar with this Vierbein formalism of general relativity and the spin connection.
So, why is it called first and second?
Yeah, first, that's a great question. So, first order, as in you on varying the action, you get first order equations of motion,
Oh, okay,
and generically in the metric formalism, you get second order equations of motion.
okay. Thank you.
Manu,
Yeah,
if you have to couple fermions to JT, then the first order is an advantage still, no?
yes, obviously. But for generic matter, for example, I think, yeah, and for fermions, we need the spin connection and all. Uh, but for generic matter, second order is definitely something more of an advantage.
Or if you want to also consider supersymmetric versions.
Yeah.
Okay.
So uh, just one word of note before we proceed, that we will not be careful about the overall numerical factor of the partition function, and because that's sort of not very important to us, but we'll be careful about other factors as we go along. So in JT gravity, we have what's called a genus expansion, and we have to sum over topologies. As mentioned before, the path integral is weighted by a factor of e to the minus s topological due to the topological term. And let me remind you that this s topological is related to the Euler characteristic by this relation. So this is what's called a disk geometry, although it does not look like a disk. Topologically, it's like a disk because it has only one connected boundary and no handles. So the Euler character of disk is 1. And then with one connected boundary, you can have a handle dug in the middle, which is obviously suppressed compared to the disk contribution, and you can have two handles dug in, which is further suppressed, and so on. And so this just goes on. So we can also consider a manifold with two disconnected boundaries like here, which we are calling the double trumpet. This is suppressed yeah, as compared to the disk, because the Euler character of the double trumpet is 0. You can dig some handle within the double trumpet, which gives a suppressed contribution, and you can dig further handles which give further suppressions, and so on. And you can have more and more connected boundaries, disconnected boundaries, and also more handles just dug in the manifolds. So we are going to study today these two geometries, which I'm going to call disk and double trumpet. So this is obviously for the simplest case, the disk geometry with one asymptotic boundary. So I told you about the Schwarzian action, and the Schwarzian action corresponds to fluctuations of the boundary and the so-called time reparameterization modes. Remember that time here refers to the Euclidean time. So this is actually an angular coordinate, and different configurations have different cutout shapes, and which will be summing over, and we'll get to it in due course. And obviously, in doing the in evaluating the disk partition function, we have to impose some boundary conditions. Our boundary conditions is simple. So our boundary is defined by a constant value of phi equals phi b, which is the value of the dilaton, with some particular length L, which is fixed. So uh, what we'll be studying here is what we call the asymptotic ADS limit. So as mentioned before, near the boundary, the dilaton and length could scale like 1 over epsilon, and also the length scales like 1 over epsilon. So this is the scaling of the dilaton and the length. And what we mean by taking the asymptotic ADS limit is that at the end of the calculation, we take this cutoff parameter epsilon to 0. So this is what we mean by asymptotic ADS limit. And in this limit, we are going to see that the first and second order results, they agree beautifully. But even for large but finite phi b and L, the path integral is rather difficult to evaluate explicitly. And this is some case of analytic evaluation. And there are subtle issues related to order of limits. So when we take in evaluate the path integral, we'll see what I mean by mode number in a moment. So we'll always work in a fixed mode number, and we'll first take the cutoff to go to 0, this epsilon. But if we did something the other way around, we might need to keep arbitrarily many higher derivative terms in the action, which we don't want to do now. So this is sort of the most precise way we can evaluate the path integral.
Sorry, what you're saying, you're putting two kinds of cutoffs. One is a UV cutoff on the modes, and the other is infrared cutoff on the volume of the.
Yeah. So in other words, we are including only the modes of the only those modes whose wavelength is much longer than the ADS length scale. Those are the modes that we are retaining.
And then you are taking the UV cut. You're removing the UV cutoff first, and then taking the infrared volume to infinity. That's what you're saying.
No, this epsilon going to cause no. Okay. So at a fixed mode number, we are taking this epsilon to 0. So the ADS length we take to infinity.
Okay, so you're doing the other way around. First taking the infrared, you're first
Yeah,
removing the infrared cutoff and then removing the UV cutoff.
yeah. Exactly. Yeah. I got confused with the UVIR. I'm sorry about that. So yes. So we want to set up the functional integration, but in order to set up the functional integration, we need some measure for the functional integration. And we take what are known as the ultra local norm for various perturbations. For example, for the metric perturbation, we have let us say we have different kinds of perturbation, delta 1g and delta 2g, and the ultra local norm is defined by this quantity. And similarly, let's say for some vector perturbations, we define a norm this way. And for some scalar perturbation, for example, for the dilatant and the Liouville mode perturbations, we would define the measure this way. And the measure that would follow from these inner products is what we are going to use for the final path integral. So it is familiar to everyone from string theory that in 2D we can write any metric GAB at least locally as a conformal factor, which is this e to the 2 sigma times some reference or fiducial metric, let's say G hat AB. And this is obviously going to play an important role in our consideration. And we now need to consider various diffeomorphisms. So the metric deformations, they admit an orthogonal decomposition. So any metric deformation can be decomposed into these parts where this is a variation of the while factor before, and then direct sum with a range of an operator P and the kernel of some operator P dagger, where the operator P is defined to act on some vector field V by this particular action. And the P dagger is the adjoint of this operator P, which acts on matrix. And the kernel of P dagger corresponds to the moduli of some particular manifold. And as it happens, there are no moduli on the disk. So therefore, we can write the path integral in this factorized form. Remember, we had this d phi before. Now we have this d sigma and dpv in lieu of the metric deformations. And obviously, we keep dividing by the volume of the gauge group. So now comes an important point, which is important for the study of the JT model. We have to sum over all diffeomorphisms V. And these diffeomorphisms, there are two kinds. One is called a small diffeomorphism and another is called large diffeomorphism. So large diffeomorphisms correspond to fluctuations of the boundary. So as I had shown you, I think a couple of slides back, so this large diffeomorphism corresponds to this fluctuation of this fluctuating boundary. Therefore, different large diffeomorphisms correspond to different cutout shapes of the boundary.
Yeah, but this word a little bit confusing, because
Yeah.
usually when you say large diffeomorphism, there are diffeomorphisms like SL, SL2Z, which are not smoothly connected to identity, but here they are smoothly connected to identity. Here you probably mean
Yeah.
diffeomorphisms which are not non-trivial on the boundary. That's
Yes, exactly, exactly. This is what we mean by large diffeomorphisms. Right. Indeed. Thank you for the comment. And large diffeomorphisms we need to sum over. So we work on the disk, and on the disk, the standard we work with the standard coordinate d r square over r square minus 1, r square minus 1 d theta square. And the boundary to begin with is located at some rb, which is much greater than 1. And this rb actually corresponds to 1 over epsilon. And what we call the small diffeomorphisms, they leave the boundary unchanged. We do not sum over them. Or in other words, we just divide out by small diffeomorphisms. And what are the conditions for small diffeomorphisms? If our boundary has some normal vector n, the small diffeomorphisms must be orthogonal to it. And also, this operator P acting on the small diffeomorphism should vanish when it is dotted with the vector, the normal vector n, and that tangent vector t. So it turns out that large
PV small
diffeomorphism.
is so what you mean by PV small is a change in the metric because of this diffeomorphism.
Yeah, 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 yeah. Exactly. This is the change in the metric.
I
Indeed,
see.
indeed.
So it will not have any leg in the normal direction. That's the point.
Yeah, yeah, yeah. Yeah. I mean,
Diffeomorphism
NA with
should
yes.
be should be along the should be in the direction should not have a component in normal direction.
Yeah. So this VA should have no component along the normal direction, and this delta GAB when dotted with this N and T, that should be 0. Yes. So large.
Sorry, could I ask a question?
Yeah. Sure, sure.
I lost my connection, so I
Oh,
missed the discussion
sorry.
about this.
Yeah.
In usual string theory path integral, when you do an integral over the disk, you don't have to worry about any large diffeomorphism, as far as I remember. It only comes when you are, say, on the torus, when you can do this SL to
So,
Z, which Oyon was mentioning. Is it because of the
so
boundary conditions
yeah,
don't allow that?
indeed. So what we are doing here is we are at first considering some cutout boundary.
Yeah.
So if in so yeah, so in string theory, what you would consider is the full disk, but in our case, our theory is defined by this cutout boundary, and this different cutout boundaries correspond to different configurations, and we need to sum over all such configurations.
Yeah, with the cutout also, that it's just topologically a disk in both cases, right? But the point is that here you are not fixing the boundary by the Dirichlet or Neumann boundary condition. You are allowing it to be of some definite shape. Is that the point?
Yes. So our boundary conditions are defined by just these two conditions, just phi equals phi
The
b.
shape can fluctuate. No? Shape can fluctuate. It's the length that is fixed.
Yeah, shape can fluctuate. Exactly, the shape can fluctuate.
So the
And the
small
large,
diffeomorphisms are those that doesn't fluctuate the shape.
exactly, precisely.
Okay, thanks.
Yeah, no problem. Thanks for the question. So now, yeah, so large diffeomorphisms, they turn out to be given by zero modes of this p dagger p, and these diffeomorphisms satisfy this condition, which in differential form notation you can call star of d psi, where this epsilon ab grad a of psi, where psi is some scalar. And when you put this VA large into P dagger P and you set it to 0, the equation that you end up with eventually the equation to solve is this grad square minus 2 of psi to 0. You have to solve this equation and then evaluate the VA large from here and evaluate the metric perturbations from the large diffeomorphisms and so on. So the mode solution, so because our theta.
Sorry, the Laplacian here is with respect to the metric that you show on the top of the page?
Yes, yes.
Thanks.
Indeed. So the mode solution turns out to be given by this, where this CM are the coefficients, and these are the different mode numbers correspond to different IM thetas. And obviously we choose the mode which are which throw away some solutions based on the regularity of the solution at the origin of the disk. So at
Upamanyu, can I add something here? Because
yeah, sure.
This mode should also be obtained independently by fluctuating the Schwarzian, right?
Yeah, yes. I mean, so sorry. What do you mean by independently fluctuating the Schwarzian?
Because the on-shell action is just the Schwarzian.
Yeah. But on-shell action is, but here we are talking about the full bulk. I mean, this is defined on the full
Yeah,
bulk.
but you're simply doing I mean, you're simply talking about linear fluctuations.
Yes,
right?
yes.
So if you take this configuration where say you take a particular shape of the boundary, which is a
Yes.
uniform like a round shape, then if you perturb that,
Yeah.
You will get these modes also, right? Isn't?
I mean, not just from the boundary, right? I mean, this is something inherently bulk thing that we are doing, and obviously we will see that. I mean, it's right here in this page that this mode we see that turns out to give the sort of the time reparameterization or Schwarzian modes.
Yeah. Okay, that's what my question was. When you take appropriately the R limit R to the
Exactly.
R lying on the boundary on. Okay, you should. Okay.
Yes, indeed. So at large R, so we insert this into that vector field. So at large R, I'm sorry, there should have been a VR large subscript here. So the vector behaves like this, and this V theta large, which is the I mean, which you can take to be the time direction, that goes like Cm hat e to the Im theta, which is precisely the fluctuation, the boundary fluctuation that we are concerned about. So we see that we get the boundary time reparameterization mode, which gives rise to the Schwarzian, as Oyonda correctly anticipated.
And then this three of them should be zero modes, is it?
Precisely.
Okay.
And we'll get there very soon. And the reality condition info actually tells us that this coefficient Cm and C minus m, they are complex conjugates of one another. So now that we have talked about this large and small diffeomorphisms for a while, we want to know whether the measure for the diffeomorphism factorizes. Whether we can write this d of PV as d of PV small and d of times d of PV large. So the answer that generally no. So there are off-diagonal terms which generally contribute, and it's in general the such splitting of small and large diffeomorphisms won't be there, and which is illustrated by the following. That, for example, in the asymptotic ADS limit, we evaluate the inner product of the metric perturbations due to the small diffeomorphism and large diffeomorphism, and we normalize it appropriately by the norm of the small diffeomorphism itself and the norm of the large diffeomorphism itself, and we are taking the square root for obvious reason. And this turns out, this goes like 1 over RB to the 3 halves. And when RB goes to infinity, the measures decouple. So it's in this limit, again, just to emphasize what was said before, it's in this limit that we are able to carry out the path integral in a nice manner. And Away from this limit, it's rather a difficult task to evaluate the path integral explicitly. So now we want to carry out the path integral in several steps. So we have the disk path integral. Let us go back to the beginning. We had delta of g mu, delta d of phi, the volume, and the action. So we'll first do the dilatant path integral. So we take phi to be some phi 0, which is some classical solution of the dilaton, and some delta phi. But this delta phi contour runs, sorry, the two should not be here, runs along the imaginary axis. And this delta phi running along the imaginary axis, you will see immediately that it imposes a delta function constraint, which simply gives some functional delta function of r plus 2. So at first we have simply gotten rid of the dilaton, and we simply have to deal with constant negative curvature space. Now, there's a pet peeve of mine that I must mention, which is that this delta phi contour running along the imaginary axis. And for those of us who have worked on the JT model in connection with nearly extremal black holes, the more natural contour should lie on the real axis, where the lower end of the contour should have some finite cutoff, where the coefficient of the Ricci scalar, which also include the ground state term, that is 0, to all the way to infinity. However, this has not been done before, and let's hope someone does it, and or I mean, even we can do it, and let's hope it's done soon, and uh, so that a more satisfactory connection to the near extremal black holes to the JT model is established. So now we come to the second step.
Sorry, Upamanyu,
Yeah.
why only near extremal black hole? I thought the Liouville mode is naturally real if it's supposed to indicate some fluctuation of the metric in 2D.
Yeah. So no, what I'm calling is this delta phi. This is along the imaginary axis. So this phi measures the volume of the transverse space.
Yeah, but that is naturally, isn't that naturally real?
Yeah, it is real, but now
But
the
is there
delta
any
phi
is there any problem in changing the contour from the real axis to imaginary axis by a rotation?
no.
Is there any,
There's no problem. I mean, the delta phi contour is taken to run along the imaginary axis. What I'm saying is that I mean, it would be more natural to do it along the real axis.
no, what I'm asking is,
Mhm.
if you think of it as a rotation from real axis to imaginary axis, is there any problem? Do you encounter any singularity or any, do you anticipate that there'll be any problem in
No,
deforming the
no, no,
contour
no.
that way?
No. In fact, this is the way we can actually do the path integral when we rotating along the imaginary axis, because this imaginary axis is what gives the delta function in a precise way along plus to minus infinity, because in delta function representation we also always have an imaginary term.
Yeah, so as a complex, on the complex delta phi plane, there is no obstruction as such in deforming the contour. So
Yeah.
there
That's
should
right.
not be any issue with that, right?
Yeah. There's no issue with that. I'm just mentioning it as a throwaway comment that it would be
Mhm.
interesting if we could do it on the real axis.
Okay.
So yeah. So now so we have this Liouville mode and the diffeomorphisms left to integrate over with the delta function constant. And now, because we have already carried out the dilaton path integral, the bulk term goes away, and even in the action, we simply have to deal with the boundary Schwarzian action. So let us now carry out the Liouville mode path integral. And in terms of the Liouville mode, the delta function, the argument of the delta function looks like this. And if we linearize it around sigma equals 0, we get something of this form with this del hat square minus 2 delta sigma. And now when we integrate over the Liouville mode, we get an inverse determinant of this operator. So which is this factor over here. And the gauge group, this omega, it is that of small diffeomorphisms, because as mentioned before, the small diffeomorphisms are what keep the geometry unchanged, the cutout shapes and everything. So we divide out by the volume of the small diffeomorphisms so as not to overcount. And now in the asymptotic ADS limit, this d of PV factorizes nicely into d of PV small and d of PV large. And there's this volume of small diffeomorphism, this determinant. So when we now carry out the integral of a small diffeomorphism, this gives a Jacobian factor of square root of delta prime of P dagger P, and we have this action. So now we have gotten rid of a lot of things, and we are going towards something nice. So again, we appeal to asymptotic ADS limit, and these determinants in the asymptotic ADS limit turn out to be independent of the large diffeomorphisms. So they are just an overall factor in the path integral that we don't care about. And the whole disk partition function reduces to this form with the measure for the large diffeomorphisms with the uh, action. So this is all that remains to be evaluated. So finally, we can find out the partition function. So the measure that follows from the ultralocal norm is this, where this mod m is greater than 2, and this dc hat m and dc m at star with this 8 pi m mod m times m square minus 1. And here Oyonda is precisely what you had anticipated, that we don't get the sum over modes where m is 0 and plus minus 1, which actually corresponds to the SL2R action. And also the Schwarzian action evaluates to this, and this J beta is what had appeared in the boundary condition for the fall off of the dilaton, and so on. And we get something nice in terms of CM and CM star. And this is just the comment that I mentioned to Oyonda, which he correctly anticipated, that for SL2R, notice that the m equals 0 and plus minus 1 sectors do not appear here. In particular, this part of the action just vanishes when m is 0 and plus minus 1, which is indicative of the SL2R invariance of the Schwarzian action. And
just one
yeah.
question, Upamanyu. So
Yes.
I was thinking somehow in this way, you don't need to physically that by force remove the m is equal to 0 plus minus 1. I thought there was some natural cancellation between numerator and denominator. Does it not happen that way?
Well, at least, I mean, no, I mean, you should not be, I mean, from the measure, I mean, you should not definitely be summing, I mean, if we take m to 0 and 0 minus 1, this measure goes to 0. But I mean, this is not done by hand. This is something that just emerges naturally, if that's what you were asking.
Well, no, in the S boundary, of course, you only sum m greater than equal to 2 because otherwise it's 0. But the
Yeah.
question is about the measure. In the measure, I thought that there would be some cancellation between numerator and denominator. Denominator has some determinant.
Yeah.
So I was asking whether there's a cancellation between numerator and denominator due to which you only take mod m greater than 2, or you are taking mod m greater than 2 just by hand.
No, oh, okay. Do you mean mod m greater than 2? I mean, just let me see. No, it naturally emerges, I would say.
But how?
Well, I mean, to begin with, I mean, otherwise the measure itself would become 0.
Yeah, that's what I'm asking actually.
I mean,
So
the measures for the 0 and plus minus modes are not there really, right?
yeah, but typically what it means is that I don't know. I mean,
I
well,
mean,
I don't know.
isn't omitting the integral over C0 and C plus minus or C0 and in this notation what was
Yeah.
m less than equal to 2, isn't that simply cancelling the volume factor in the denominator? These are the integral over the zero modes, right?
Yeah. So these are okay. So if you like, I mean, so these SL2 volumes, they are not part. I mean, okay, yeah, okay. And now I see what you mean. So yes, I mean, if you say that you want to divide out by those volumes, then this is done in a natural way. But we did not proceed that way. So yes, I think yeah, your point is well taken.
Yeah, indeed, it should be cancelled by the volume. Indeed,
Yeah. Yeah, I mean,
volume
yeah, I
by
mean, because we did not write the SL to our volume itself in the first place, so I think that would take care of it this way. Yes, indeed. So now the path integral, it's a very nice Gaussian and it's easy to carry out, and we obtain the following partition function for the disk, and we get agreement with the first order result of Shad, Senker, and Stanford. And here notice that we have reinstated the topological term, and they just follow naturally. So at this point, before I go on, I would like to ask if there are any obvious any questions that I should be addressing at the moment.
Yeah. So one question here. So you said first order in what? First order of Schenker et al. Result in what? So
First order of Schenker result is precisely this
no,
for the disk partition function.
but first order in what? First order in what expansion?
Oh, sorry. In the first order formalism with the spin connection and the Wehrbein. I mean, so we were dealing with the metric and dilatant directly, and they did it with the very elegant mathematical machinery of the first order formalism and uh, some nice mathematical results, which are actually due to Wheaton from early 90s. And from there, they evaluated the partition function, and they did get this. I mean, obviously, we are not being careful about the overall factor of the partition function, but that's about it.
No, but actually this is something I don't understand. You have not done the integral in the middle. In the bulk part, you have not done. You have essentially done the integral at the boundary. You have done the path integral, which is essentially coming from the large modes.
Yeah. So that is the point. So essentially, that's the point, because the dilatant integral, when we carry out that, sorry, miss it. Yes. So when we carry out the dilatant integral, the bulk part is set to 0. So there's no bulk integral here to do, because this dilaton multiplies this r plus 2 linearly.
No. This is not the point. Okay, but then this separation. So, okay, yeah, this I understand. So you restrict yourself to r plus 2 equal to 0 surface. That I
Yes.
understand. But on the r plus 2 equal to 0 surface, there is a small diffeomorphism, there is a large diffeomorphism.
Yes.
So this separation between small and large, you argued that it is not possible in general.
Yes.
But then you took a limit.
Yeah.
So what is the physics of that limit? I mean, that limit somehow that limit did not play any role. You got the exact answer in the end.
Yeah. So it's in that limit that we got the answer. So that limit did play a role. So that limit played the role in going from this step here to this step here.
Yeah.
Otherwise, this from this step, this general diffeomorphism, it's in this asymptotic ADS limit. This factorizes. So
Yeah.
this limit actually plays, I mean, a crucial role.
Yeah.
Otherwise, I mean, without this factorization, the small mixes with the large in some very complicated way, and
Yes. So
yeah.
Shankar et al. Has a more complicated answer,
Mhm.
which but by some expansion, you recover your answer. By doing some expansion in that answer, you can recover your.
Yes, yeah. Yeah, I mean, so it's in, I think their answer also is the asymptotic limit.
Their answer is also in some asymptotic limit. Actually, I'm not.
No, I think they have the same answer, Amitav. I think the point here is that somehow in this when you take the infrared cutoff, when you remove the infrared cutoff, the bulk only contributes a number which is irrelevant, which they haven't compared with, I think, the Schenker method.
Yeah.
But other than that, the answer, the dependence on beta, that is L,
Exactly.
is the same.
Yes.
Yes.
This beta dependence is what we wanted. And this is also one loop exact as was argued by Stanford and Witten in a paper of theirs from 2017.
Actually, this limiting in between this limiting process, I am not understanding. What is that limit? The limit where you separate the small versus large.
Yeah. So, yes, this.
Yeah,
Right.
this exactly. This RB becoming large.
Yes. So we deal with some fixed mode number, as Oyanda was putting it in the language of UV and IR. So with the fixed mode, we take the IR limit first and taking the RB going to infinite limit, and then we take the UV limit, and we can do the we can yeah. In other words, for a fixed mode number, taking the asymptotic radius limit gives us simply the Schwarzian. But let's say if we are doing it the other way, then we would have to keep arbitrarily high powers of the derivative to make sense.
RB is the location of the boundary.
Yes, RB is the location of the boundary. RB is 1 over epsilon in the language that in the language of the cutoff that I had introduced previously. Is that okay?
Okay, fine. Actually, I am sorry, I am unable to understand the picture because I mean you are supposed to do integral over the disk, and now somehow you are converting that integral to the boundary, and then saying that I will take the limit boundary going to infinity.
Yeah, I think the point is that because of this, because the small and large diffeomorphisms become orthogonal to each other in this infrared limit, when you remove the infrared cutoff,
Yes.
the bulk only gives you an overall number, which they are not caring about.
Exactly. Exactly.
Okay, so
Indeed.
this statement, yeah, this statement I understood, but what allows us to do this separation in the first place?
Yeah, I think this is okay. So this actually is the standard, I think, way to proceed. Like you take arbitrary fluctuations of the metric and try to decompose them into orthogonal components, no? And now here you cannot do it, but unless you take the infrared cutoff to unless you remove the infrared cutoff, so they're doing it in that way. Yeah, so I think that's what they're arguing.
Yes. Yes. Yeah. Thank you for the comment, Hayanda. So should I proceed?
Yes, yes.
Yeah. Yeah, and I'd be happy to answer any question afterwards also, but I'll just yeah. So now we want to add matter fields. Let's say some scalar, some massless scalar, which is conformally invariant. And the path integral now also involves the matter field. So now we have this this phi integral with some action of this with some action, which is this action basically. And the matter path integral is easy to carry out, and this matter path integral gives 1 square root, and we have some. So it turns out that even in this case, in the asymptotic ADS limit with Dirichlet boundary conditions for the matter fields, this determinant turns out to be independent of the large diffeomorphism. So the result for the partition function turns out to be the same.
I just want to
Yes.
make a comment here,
Yes.
Upamanyu. So I think there should be a restriction on the scaling dimension of the matter field, because otherwise it changes the boundary condition for dilatant, which we found out.
I see.
If you look into our paper,
Okay. Okay.
unless there is, so the asymptotics of dilatant changes,
Mhm.
unless you put a restriction. I forgot exactly what it
I see.
was.
Yeah, I mean, it's okay. I assuming some conditions on the matter fields and so on that we get this result. And now let us come to. So I think I'm nearing the end of my talk. So can I go on for a little bit more? Is that okay?
Sure.
Okay.
Actually,
Yeah. So
one question here.
yeah,
This
please.
scalar field result, does
Yeah.
the Schenker group are they able to get this result using BF theory?
No. This is sort of the point of our doing this.
Yeah. Because SL2R, so they use this very precise mathematical structure which is tied to the number of fields and so on.
Yeah. So basically, they are able to write down the spin connection and the Vierbein in terms of uh, in terms of a matrix of an SL2R matrix, and they write it as BF. They integrate out. So when they perform the path integral, they get integral over flat connections and so on. So yeah, they did not have anything about matter. So now we want to do the double trumpet, which has two asymptotic ADS boundaries, and there are two Schwarzian theories living on the two boundaries. And the metric on the double trumpet, we can take it to be of this form, and theta is identified with theta plus b. So the new element is that it has two moduli, which is the size of this circle b, and a relative twist, which is sort of, you can imagine as the two boundaries being twisted relative to one another. So these are the two moduli that we have to sum over as well. So again, in the double trumpet path integral, we consider the asymptotic limit with two boundaries, where this dilaton has these forms and the lengths have these forms, and at the end of the calculation we take this epsilon1 and epsilon2 to go to 0. And the path integral now involves an integral over the moduli space. So in addition to what we had previously in the asymptotic limit, we also have because the measure comes out to be b db, and this, remember, is an ordinary integral, not a path integral. And when we carry out when we compute the path integral, the partition function turns out to be given by this quantity, where this beta 1 and beta 2 are what had appeared in this expressions involving the dilaton. And this is sorry. And this is indeed the expression that Sad, Shankar, and Stanford get up to some overall constant that we anyway did not care about. So now comes the important part. So this is one of the key results, that when we consider the double trumpet with matter, there's a trouble. So the scalar partition function gives for small b this quantity. It goes roughly like this. And because of the Casimir energy of the scalar, so the path integral with one scalar gives a divergent contribution for small throat size. So the moduli space is integral from for b from 0 to infinity, and it has b to the 3 halves and e to the pi square over 6b. You see that this has an essential singularity at b equals 0. So it seems that the path integral is not well defined. So this is something that obviously needs to be looked more into. You might worry that this b to the 3 halves in the other opposite limit also has a similar problem, but no, because it turns out that there are other factors in the expression, which is some e to the minus pb square, where p is some positive number, which makes the large B behavior well defined. Yeah.
Upamanyu.
Yes.
Earlier you mentioned that there's a proof by Witten and Stanford that for the pure JT gravity,
Yeah.
you have one loop exact answer.
Yeah.
So there's a localization on the
Yes.
on this r plus 2 is equal to 0 like thing.
Yeah.
What about if you add matter? Does the result hold that, which can allow such extra terms to appear?
I don't think there's any result to that effect, to my knowledge. I'm not sure of that. I think, I mean, with matter, I think all bets are off. I mean, it was in the pure Schwarzian theory that their result was true. Uh, I'm I'm not sure about the answer.
Okay.
So I mean, what our result at least indicates is that the path because of this essential singularity, that the path integral itself is probably not well defined.
Wait,
And
I just want to make a small-ish
yeah,
comment, but with matter, certainly you should have probably other effects,
yeah,
which is beyond just linear fluctuations, right? Because
hmm,
you have things like this Lyapunov growth coming precisely from 4 point,
I
which
see,
which do not really which has a which is not simply uh, uh, it's not simply like Gaussian. There is a connection. It's a connected diagram that leads to this Lyapunov growth from the
I
bulk
see.
perspective.
Okay, I see. Yeah, thanks for the comment. We'll try to look into it. So one might think that there's some way to circumvent this problem with fermions, but I mean, if you take, for example, antiperiodic fermions, which are antiperiodic along the theta direction, and also antiperiodic along the radial direction, you get some very similar divergence. So this antiperiodicity is natural in this case because we want to compute the partition function and not index. So I mean, this divergence can be removed for some cases. For example, where you consider periodic boundary conditions for the fermion, which would roughly correspond to an index and not a partition function. So we are not yet sure what to make of this result, and the interpretation of this result is rather a rather open problem that we found. And before I come to end, let me also discuss briefly de Sitter JT gravity, which we also addressed in our paper. So there's JT gravity with a positive cosmological constant developed as well. First, I think by Maldacena, Tudiachi, and Yang. And there, instead of the partition function, one calculates the wave function of the universe. And it might be known to many of you that it is known to many of you that there's an additional element in such case, that the integration contour involves manifolds of different metric signatures, and we'll see a picture soon. And there are many similarities to the ADS case in the asymptotic limit. So this is what we call the de Sitter disk, and there are sort of two contours. So one is, for example, just the Euclidean sphere, our good old friend, and we just cut it and paste it to Minkowskian de Sitter, and we evaluate the wave function for some large values of the size of the universe. So this is what we call the 2,0 contour, which is the segment of the sphere joined to the Minkowski de Sitter. So Maldacena and friends pointed out that there could be yet another contour which gives very sensible results and which is actually very useful, which is called a minus ADS 2 contour, which involves some contour which has negative definite signature, which has the metric signature minus minus, and uh, then with a suitable analytic continuation, a Minkowskian DS can be obtained. And we found that for both of these contours, the result for the wave function of the universe turned out to be the same. And we also consider what's called the de Sitter double trumpet, which is this ADS2 double trumpet, and the two ends continue to de Sitter. And this measures the probability amplitude for two disconnected universe being created. And this is some interesting result. And here too, because of the Casimir effect, we found a divergence as we found in the ADS double trumpet case. And obviously more work, it opens up a whole lot of work that could be done in this direction. So I am at the end of the talk. I'm sorry I took a little extra time. So in conclusion, second order formalism for JT gravity gives the same result as the first order formalism in the asymptotic DS or ADS limit. And this formalism obviously allowed matter to be incorporated directly. There are interesting results, especially some divergences that appeared, which are very interesting results in themselves. And they also invite more and more new questions, and there are many aspects to explore in these regards. And it would obviously be nice to understand the path integral for these cases away from the asymptotic limit, especially in the context of cosmology, where we have some finite size of the universe. So with these words, let me thank the organizers again, and I would like to definitely answer any question that anyone might have till the host decides to close this meeting. Thank you very much.
Thank you, Upamanyu. Very nice talk.
Thank you very much.
So time for questions indeed. Let's
Yes.
have you.
Yeah, I don't see any. So let me go to this.
Upamanyu, can you say just for me to understand a little bit more? Can you say a little bit more on this asymptotic DS or ADS limit, because I'm still not understanding this.
Okay. So okay, okay. Let me go back. So, I mean, please, I mean, defined this way, this is what corresponds to the asymptotic limit. The length of the boundary scales like 2 pi over epsilon, and the dilaton goes like 2 pi over j beta epsilon. And what we mean by the asymptotic limit is when both of these go to infinity in this coordinated way, when epsilon to 0. In other words, you can say that we take the asymptotic limit where the length of the boundary goes to infinity and the dilaton of the boundary goes to infinity, so that the ratio of L to phi b remains fixed. This is what we mean by the asymptotic limit.
So the path integral is a functional of phi b. Is this
Yes.
how is okay? So this is how I should think of.
Yeah,
So
it's a function of phi b and also L. Yes, yes.
oh, I see. Okay, so now I understand.
So these are the two boundary conditions that are fixed. So our path integral is with a fixed length of the boundary and some fixed phi b.
Okay, now I understand.
Yeah, thank you. Yeah, anyone else?
I have a kind of confusion here. So
Yeah.
actually, I've seen people take this limit, where you keep the length fixed of the boundary.
Yeah.
But yeah, I think it's sort of little bit artificial. It's not in the original, like in the usual formulation of the thing. But I think the understanding is that somehow each of these define a state, a kind of, and these are what people call, I think, fixed areas.
I see. Fixed area states in quantum gravity or something.
Yeah, these are the definition of states. It's not quite clear to me whether these states are enough to, like generically give a basis of states in the full Q quantum gravity.
I see.
So this is something, at least, okay, perturbatively it should, but I'm not sure whether that's a kind of, maybe I always have a little bit, even I see when people do many of this connections between quantum information and gravity, they use this kind of basis of states many times. So, okay, at least in Euclidean context, that's what people do. So I'm a little bit unsure whether whether this is really gives you I haven't seen any proof anywhere it can give you a total basis of
Yeah,
state.
that's an interesting point. I mean, I haven't thought about it at all. I mean, I have I mean, I haven't studied those papers, but yeah, I mean, it would be nice to look into them indeed.
And for the DS case, exactly what is this an analog of this L? I didn't. So
L is the size of the universe.
it appears in this ADS2 minus minus, also appears in the S2 point of view.
No, no. Okay, sorry. This is in the asymptotic DS region. So let me go there. So, yeah. So we can have some cutout surface here. So this measures this length of the universe, the size of the universe, and there the phi b or the phi that's the dilaton gives you a natural clock. So phi is the clock and L is the size of the universe.
Okay.
So yeah, let me should I try to annotate?
No, I got it. I got
Yeah,
it.
okay. Yeah, thank you.
Okay, Upamanyu, one last random question.
Mhm.
Is there any relation to sense quantum entropy function formalism of any of this?
Well, I mean, not. I can't think of a direct relation between this work of ours and quantum entropy of Professor Sen. But I mean, we did do some work in JT gravity for rotating black holes, where the relation we explored the relation briefly in some earlier paper of ours. Yeah, but I mean, in this particular case, I am not sure at the moment, and I will have to think about it before I get back to you.
But morally, there should be a relation, right? Because although sense talks about a strict limit t goes to 0, you have a bit near extremal. So
Yeah.
actually, we're computing the near extremal quantum entropy in a way.
Yeah, yeah. One more, yes,
There
yes,
should be some relation.
yes, yeah, yeah, yes. Morally, indeed, indeed. Yeah, I mean, we did not couch it in this language, but indeed, I mean, there has to be, right.
Yeah, in this context, this having a fixed L, I don't know what's the interpretation actually. Whether it's something that can be naturally incorporated, sense way of thinking. That was the only that is sort of the only point where I feel a little bit uncomfortable.
I see. Yeah, and obviously, I mean, this is something to think about.
So, any further question? You still can have one or two more, if any. Okay, then since there are no further questions, Amitav has a question. Amitav just claps. Okay.
Thank you very much.
All right. So claps again, and,
Thank you.
and thanks for this nice talk. And see you all then next week on Monday. There's a talk by J.R. Muss, and then there'll be a talk on Thursday by Michal Heller on his latest paper of quantum circuit modeling of space-time. Okay. So
Thank you, Upamanyu.
Thank you very much. Thank you for your questions, and it was really enriching for me.